Hello and welcome to the lectures on state space approach to control system analysis and design. In this week, we are discussing the design of controllers based on multi-rate sampling. And the topic in today's video is periodic output feedback controller. So in this week, our focus is on a special class of sample data control systems in which the sampling rate for inputs and the sampling rate for outputs are different. They are not equal. We are concentrating on this type of controllers. And in the previous two lectures, we considered the multi-rate output controller, abbreviated MROC, and the fast output sampling based controller, or the FOS controller. And in both of these, the rate of sampling the output was faster compared to the sampling rate for the input. So during one interval, sampling interval corresponding to the input, the outputs were sampled several times during that. These two controllers we discussed, the MROC and the FOS. And in case of MROC, this input sampling rate is T0, the output sampling rate is T0 by N1, T0 by N2, etc. And the control system is a dynamic control signal computed using the previous value of control signal and the multi-rate samples of output. This is just a recall. So MROC was characterized by this, that it is a dynamic controller. The the value of input k plus 1t is dependent on the previous value of input and again multiplied by the samples of output. And sampling rates of different outputs, they were different. So output 1 was sampled at T0 by N1, this was the time period, output 2, T0 by N2, and so on. So in the multi-rate output controller, the output sampling rates for different outputs were different, allowed to be different. Then we discussed the fast output sampling based controller. This is very similar and can be regarded as a special case of multi-rate output controller. In this one, the input signal is computed based upon the control signal. In this case it is non-dynamic, it is static. So previous control signal, that knowledge is not required. Only it is calculated based on the samples of output collected a number of times during one sampling interval. So several finer space time instants, at those instants the outputs are collected and from that the input is generated. And the only difference from MROC is that the output samples are taken at the same rate for all the outputs. In MROC they were N1, N2, N3, etc., where the number of samples in one sampling interval of input. Here it is N for all the outputs. All outputs are sampled at the same rate, N by T, 0. If T0 is the input sampling rate. Again there is a misprint here, it should be UKT0. I'm sorry for this misprint. So that is in what sense FOS and MROC are different. And of course, as I told, the control signal is non-dynamic in case of the fast output sampling based control. Remember, in fast output sampling, the input samples were collected at a larger intervals of time t, and the outputs were sampled at the rate delta. However, in periodic output feedback, the input is updated several times during one interval t. So, the distinguishing feature of periodic output feedback controller is that the output is sampled at a slower rate 1 by t per second, and the input is sampled at a faster rate 1 by delta per second, and delta is t by n. N is an integer which is greater than 1, of course. So the inputs are sampled at several uniformly spaced instants of time during one output sampling interval. This is one feature. Other thing is that control gains, we'll see, I will explain this, they are periodically varying. That means control gain at some time is equal to the control gain sometimes in the past, and it will repeat again and again. I will show with the help of the mathematical expression. And it is having the same power as MROC or fast output sampling controller. This controller can also achieve arbitrary pole placement. In fact, we will see that it can place poles even if the poles of the closed loop system are at origin of the Z plane, which fast output sampling controller did not allow because of the matrix invertibility issues. So in that sense, POF controller, periodic output feedback controller, is little better than the fast output sampling controller. So we now proceed to see how a periodic output feedback control looks. So we have again the continuous time system x dot equal to x plus bu with the output equation y equal to cx. System order is n, number of inputs is m, and number of outputs is p. And we have its corresponding discrete time system for two sampling rates. One sampling rate 1 by t and other sampling rate 1 by delta. And recall that phi t is e power at, and gamma t is integral between 0 to t e power a tau b d tau. Similarly, phi delta and gamma delta can be given. In place of t, we will have delta. That is the difference. So we have the same continuous time linear time invariant system, and we have the corresponding discrete time systems for the two sampling rates, one 1 by t and the other 1 by delta. And the output sampling rate is 1 by t per second, which is divided into n subintervals, each of size delta. So basically this is the t, this is kt, and this is k plus 1 t. This is one sampling interval of output, and this is divided, this is each one of this is delta, this is t. So this is kt plus delta, this one is kt plus 2 delta, and so on. This is kt plus n delta, and because delta is t by n, so it is k plus 1 t. So in one sampling interval of output, we have agreed to divide and obtain n subintervals, and at each end of each subinterval we will change the input, as given by this. The input between Kt plus L delta, let us say here this is Kt plus L delta and this one is Kt plus L plus 1 delta. So during this interval, the input is again KL times YKT. YKT is here. At this instant the output was collected, YKT. That multiplied by again KL is the input here in this period. So for example, if L is 0, we will have from KT to KT plus L delta, or KT plus L is 0. So during KT to KT plus delta, we will have the input given by ut equal to K0 into YKT. At the next interval for L equal to 1, that means from KT plus delta to KT plus L delta, KT plus 2 delta, the output will be given by that ut during this period will be given by K1 into same output sample. So the output sample which was collected here at the KT multiplied by that by different gains, we obtain the inputs. So if I show graphically, so let me just say that this is KT and this is K plus 1T, and we have, let me also show K minus 1T. Let me draw a little better figure. So we have K minus 1T and we have KT and we have K plus 1T. Now we sampled the output here. This is the output sample. So during with a zero order hold, this is YKT. And we have divided this subinterval, let us say, in this many 1, 2, 3, 4, 5, 6, 7 subintervals, each of delta. So delta is T by 7 in this diagram. It will be T by N in general. And we have gain K0, K1, etc. up to K7 in this case. So input during this interval will be YKT. This is YKT multiplied by K0. Now in the next subinterval, it will be this value, which is K1 into YKT. The value of the output is same, but control gains can be different, K0, K1, etc. In next subinterval, it will be K2 times that YKT, and so on. So for the same value of the output, different control signals are generated to be applied in different small subintervals of time. So this is K0 into Y there, K1 into Y, K2 into Y, K3 into Y, K4 into Y, K5 into Y, K6Y, and K6Y, because these are 7 subintervals, so it will be from K0 to K6. These are the 7 blocks of gain scale. So this is how the input is generated in the periodic output feedback control. And now I explain here that what is the meaning of periodic. It is this. Substitute L equal to 0, we'll see that Kn is same as K0. Substitute L equal to 1, we will see that Kn plus 1 will be same as K1. Substitute L equal to 2, Kn plus 2 will be same as K2. So the gains in one interval are K1, K0, K1, etc., Kn. In the next interval again they will be K0, K1, etc., K. So the control gains, that is how they are periodically time varying. They are varying with time, however periodic in nature. K0 and Kn, K2n, they will be all identical. K1, Kn plus 1, K2n plus 1, they will be identical, and so on. So we have the same set of n gains repeating in each output sampling interval. That is the meaning of the periodic. And piecewise constant, the gain is same during one delta interval. So this is piecewise constant and periodic varying gain in case of the periodic output feedback control. This is the essential characteristics of periodic output feedback control. And of course the input is updated n times, n is an integer in one output sampling interval in each one. This is further POF controller, the periodic output feedback controller, can be explained with help of this block diagram. The input is sampled at every delta. Delta is T by N. And output is sampled every T second. So at the end of the time period KT, at the beginning of, so here we have YKT. And that value is multiplied by again K0. The same value is multiplied by K1. It is the same signal multiplied by K0, K1, K2, etc., Kn minus 1. This is set of n gains. And they are made available here, let us say. Now, at KT plus 0 delta, KT plus 0 times delta, the input will be generated by this K0YKT. So as if this switch is here, this selector is here. At the end of that delta, that means at the beginning of KT plus 1 delta, next subinterval, the selector will come to this position and it will take K1 times YKT. Again after delta time, the selector will take this position and it will apply K2 times YKT here, and so on. So in the periodic output feedback control, as I explained earlier and is evident in this block diagram, it is the same sample of Y, however control signal is generated by multiplying that Y by different gains and applying that several times into one sampling interval T. So at KT plus delta, at KT plus 2 delta, and so on. Input is updated n times based on the same sample of output. This is a periodic output feedback, and this is periodic output feedback and fast output sampling feedback controller can be considered as dual of each other. So now we derive the expression for periodic output feedback control gain, that K0, K1, etc. We are going to now derive mathematical expression for that. And for that, we start with the state of the system at different subintervals. So we consider the value of state at kt plus delta. It is phi delta, the value of state at kt, and gamma delta into the input at instant kt. The state of the system at kt plus delta is being given by this. At kt plus 2 delta, the state will be phi delta into state at the previous instant, and we are considering the time instant separated by delta, the subintervals. So phi delta into x at the previous instant plus gamma delta u at the previous instant, and this one we have here. So we can substitute this expression in this one, and then we will have this expression. Phi delta into this is expression for x kt plus delta, and this is here. This we can further manipulate to obtain phi delta square. This and this will give phi delta square x kt here, and then phi delta gamma delta into u kt, and then this as it is. So this becomes the value of the state at the x kt plus 2 delta. So this delta are between kt to k plus 1 t here. So this is delta, this is 2 delta, etc. So we are considering the values of the state at these sub intervals, and they are this. In this manner we can derive x and come to x kt plus n delta, which is, this was kt, this is kt plus n delta, which is same as k plus 1 t, because delta is t by n or t is n delta. So this state here in that manner will be given by this expression, phi delta power n into x here plus this into uk delta, this into kt plus delta, and so on, gamma delta into this one. So that inputs, the value of input, this one, this one, this one, etc., which are generated from the sample of output at kt multiplying by k0, k1, k2, etc. So that gives this one. And once we obtain that, then the input is, because it is k0 times ykt, so it is k0 times cxkt. Y is cx, so k0 cxkt. At the next sub instant of time, kt plus delta, u will be k1 times ykt, and so k1 times cxkt. We are considering the output at kt instant only. So ykt is same as cxkt, and so we have ukt as k0 cxkt, ukt plus delta k1 cxkt, and so on we will have. Next input will be k2 times cxkt. In this manner we can go on, and we have the input in the last sub interval. This is kt to kt plus delta, this is kt to kt plus 2 delta, and so on. The last one, kt plus n minus 1 delta. This will be kn minus 1 into y, which is cx. So in this manner we have the values of input at during these subintervals of time. So based on these, that means we can have x kt plus delta from x kt, and this is the value of the input. This is y, and this is multiplied by gamma delta. So we have the x kt plus delta Similarly, x kt plus 2 delta, and so on. In this manner, we will have x kt plus n delta given by this. And now we start taking a look. So this one is containing phi delta x kt. This one is containing, this is 2 delta here, so phi delta square. This is n delta here, so phi delta power n. And this is only delta, so it is gamma delta into k0. Here it's 2 deltas are there, so gamma delta k1 and gamma delta k0. Here n are there, so we have gamma delta k0, gamma delta k1, and so on, gamma delta kn minus 1, and of course each one re-multiplied by phi delta square, etc. So based on that expressions we can write in concise form like this: xk plus 1 t, here this is kt and this is k plus 1 t. So at the end of the subinterval t, the state x will be given by this phi delta is the STM corresponding to a smaller interval of time, delta. So phi delta power n plus gamma kc into xkt. This is essentially coming from here, coming from these expressions. So the moment we write what are that gamma and k, it will be clear. Gamma is that matrix. Gamma delta, phi delta, gamma delta, phi delta, gamma delta, and so on, phi delta, n minus 1, gamma delta. So this is these products assembled together, all these columns assembled together is the boldface gamma, and k is those gains, k0, k1, etc., those set of n gains. C is the output matrix. So this follows from the previous slide. From these expressions, those come. X k plus 1 t is x at the preceding sampling interval at the rate 1 by t multiplied by phi delta n, and then this product. This is this. This is this. Now at this point we hold the equations there and we think of a gain g in phi t plus gc, such that this phi t plus gc, this system will have desired pole locations in the unit circle, because we are talking of discrete time system, so we are talking of unit circle in the z plane. So we assume existence of a g for the system phi t c. It is not phi t gamma t, please mind it. Phi t gamma t is the coming from the state equation. Here it is c coming from the output equation. This one. So we take phi t and we take c and we assume that there exists a g such that this system will have desired pole locations. Of course, this is same as phi t transpose plus c transpose g transpose. So if we consider the dual of the system phi t gamma t c, and for the dual system means in which phi t transpose and c transpose are considered respectively as system matrix and the input matrix, we are designing a controller g transpose, which will be the gain. So in this case we call it as a output injection matrix, output injection gain so we design a G, the output injection gain G, such that the poles of this system will be at the desired locations in the unit circle. That is done, and of course we have this relation phi t is same as phi delta power n. So we compare this system which we obtained in one of the previous slides and this closed loop system with phi t substituted by phi delta power n, and we see that the two systems will be same, behave similar, means state at next time instant will be same if this matrix and this matrix are equal, and means that gamma c, gamma kc and gc should be equal, and that means that gamma k should be equal to z. This is the expression for the periodic output feedback gain, and this should be solved to get k. And of course gamma is this. So we can immediately see that this matrix will have full rank if n is greater than or equal to mu, and mu is the controllability index of the system, meaning that phi delta mu minus 1 gamma delta, phi delta mu minus 2 gamma delta, and so on gamma delta, this rank equal to rank of phi delta power mu gamma delta, phi delta mu minus 1 gamma delta, and so on phi delta gamma delta gamma delta. So this mu, sorry, all these are mu. So this mu is that largest integer for which rank of this matrix and rank of this matrix are equal. That is the controllability index, how it is to be taken here. And if we choose n satisfying this greater than or equal to mu, then gamma will be a full rank. And if gamma is a full rank, means gamma inverse will exist, and means we can solve this equation. It is so, that is one thing. And how we can obtain G? G can be obtained if phi t transpose C transpose is controllable, or if phi t C is observable. So if phi t C pair is an observable pair, then G, solution of G can be obtained. A G can be designed either by pole placement method or by linear quadratic regulator design to obtain the poles of this system at the desired location, or to optimize a cost function. Whatever way, a G can be obtained if this phi t C is observable matrix, observable system. So the solution to gamma k, this bold gamma k equal to G will exist if the system, if n is chosen to be larger than or equal to the controllability index of the system, and if the system sampled at the rate 1 by t is observable. In that case, gamma will exist. This is summarized here, that the sampled system should be controllable and observable, and number of subintervals in t should be larger than mu, the controllability index. Then the solution will exist. And of course, now there are two possibilities. If n is exactly equal to mu, then the solution will be unique, because gamma is inverted, number of unknowns is equal to number of equations, and gamma has full rank, so its inverse will be obtained. And so solution of k, this is not gamma, this is k, solution of k will be unique. However, if n is larger than mu, then sum of the gains k are to be assumed, the number of equations are fewer than the number of unknowns, and that means we can have extra considerations in the periodic output feedback gain design. So some k are to be selected differently and remaining are to be solved from the equations. So in this manner we can solve this for both n greater than mu as well as n equal to mu. Solution will not exist for n less than mu. We are constrained to select n greater than or equal to mu. Now we see with the help of same example, for which we consider the fast output sampling based controller. We consider that system. This system, when discretized for sampling period equal to 1 second, gives this state transition matrix or the system matrix, and this as the input matrix, phi t and gamma t. And using this phi t, this c, we can design a G, and we see that this G places the poles of this phi t plus gc at these two locations in the z plane. Both of them are less than 1, and so the system is stable. It may be satisfying some transient performance characteristics, but just for the purpose of demonstration of design of periodic output feedback controller, we consider G to obtain these pole locations for phi t plus gc. Once G is there, then next job is to obtain K. That will require the phi delta and gamma delta. So we select n equal to 2 sub-intervals in each output sampling interval, and the delta becomes t by n, t by 2, and so 1 by 2, and that gives 0.5. And for that, this is the system matrix of the discrete time system, this is the input matrix for the discrete time system corresponding to that continuous time system in the example. For the sampling rate, 2 per second, 2 samples per second. So then this bold face gamma is phi delta, gamma delta, and gamma delta, 2 columns, these. And then K is obtained as gamma inverse G. G was there in the previous page. So gamma inverse G, which is this. And this K is the required periodic output feedback gains. It will have the same pole locations as the pole locations which this G gives for phi t plus gc. This K will give the same pole locations for phi t plus gamma k c. So we obtained that. We consider another design in which we select 4 subintervals into one output subinterval, and then delta is 1 by 4 or 0.25, and for this we have this phi delta and this gamma delta, and G is same. This bold face gamma is now 4 columns, gamma delta, phi delta, gamma delta, phi delta square gamma delta, phi delta cube gamma delta, and these are these 4 columns are these 4. This we obtain from this phi delta and this gamma delta. And now if we evaluate gamma k equal to G, solution to this, now gamma is a rectangular matrix, and so several inverses are possible. So what we do is, this K, which will have now 4 elements K0, K1, K2 and K3. We can select any two out of this and remaining two we can determine. So in this case, this K1, K3 and K2 and K3 were selected and K0 and K1 were obtained by solving the equation gamma K equal to G. So basically that if this is gamma 1 and this is gamma 2 and if this is K1 and Ka and this is Kb, so gamma 1 into Ka plus gamma 2 into Kb. So in this we assumed Kb, so gamma 2 Kb is known, that is subtracted from the right hand side. So G minus gamma 2 Kb, that is equated to gamma 1 Ka, and so Ka is obtained by gamma 1 inverse G minus gamma 2 Kb, and this is Ka and this was assumed. So out of 4, because we had only 2 equations, 2 we assumed and remaining 2 we evaluated from the 2 equations. We could have chosen any 2, or we could have chosen different values of these 2 itself. So numerous solutions for K is possible implementing the same output injection gain or achieving the same closed loop pole locations, multiple choices. So based on other considerations, one can see which of those multiple selections of K, multiple choices of K is a better design or the best design. That can be obtained based on some other consideration. Now we summarize. In periodic output feedback, the input is updated several times during each output sampling interval, and any output injection gain can be realized, and poles of the sample data system for the sampling period T can be placed at any arbitrary locations as desired, and here also observer is not required. So we conclude this multi-rate sampling controllers with 2-3 more observations. First thing is that we considered MROC, multi-rate output controller, the controller in which each output could be sampled at different rates and input was sampled every larger T interval T. Then we consider the fast output sampling controller. Each output is sampled at the same rate n by t. Here it was n1 by t, n2 by t, etc. Here it is for all outputs the rate is same, n by t. And then we considered periodic output feedback, which is dual of fast output sampling. In fast output sampling, the output sampling interval are smaller. Output is sampled several times during each sampling interval of input. In periodic output feedback, the output is sampled at larger intervals of time and input is sampled several times during one sampling interval of output. We considered these 3, and each of these 3 is capable of achieving complete pole placement for the sample data system corresponding to the continuous time system. Of course, in FOS and MROC there were certain restrictions. We could not have the poles at the origin of the Z plane for the closed loop system. In periodic output feedback, that restriction is not there. Each of these is targeted to avoid the design of an observer which has issue. We saw that observer design, first thing, it increases the complexity of the overall closed loop system, the order of the system. And second thing, we saw that it could be susceptible to small variations in the system matrix or output matrix or noise, etc. Here also some of those issues will remain, but observer design is not required. The order of the final system in case of fast output sampling and periodic output feedback is unchanged. In MROC, it is because input is also generated through a dynamic system. The order of the closed loop system is larger than n, the order of the open loop system. Now all these three are very attractive because these days the controllers are implemented using digital computers. So naturally there will be sampling and there will be samples of input taken, output taken, etc. So in these days there is no implementation issue as far as these controllers are concerned, and they emerge to be natural choice. One can consider these designs in place of the design of controller and then accompanied with design of observer based on the continuous time system description. One can select this. This fast output sampling controller is seen to give little better response compared to periodic output feedback controller, especially because this periodic output feedback controller, the input is K0 times YKT, let us say, then K1 times YKT and so on. And because this K0, K1, etc. are different, during each subinterval, the input will jump from one value to other value to other value and so on. And these jumps may be undesirable. Also correspondingly, the values of states at xkt plus delta, xkt plus 2 delta and so on, these states will show a lot of variation, and of course the specification of output at ykt, they will be satisfied. So one observes that in case of the periodic output feedback control, the response of the system at the output sampling intervals is very smooth. At the sub-intervals, there can be jumps in the control signal, ukt plus delta, 2 delta, etc., as well as in the values of the states. So this may not be desirable in certain situations. Otherwise, periodic output feedback controller is the simplest in these three. In fact, periodic output feedback controller is the simplest, and multi-rate output controller is the most complex out of these three. All three, of course, they are implementable through the use of digital control system, discrete sample data control system, and by incorporation of digital computers in the loop. Thank you very much. We'll meet again to discuss a different topic.